Hi, in this session of finite element analysis of beam, that is fourth session, we are going to solve a problem based on whatever the theory we have covered in last three sessions. Using that, we are going to solve the problem in this session. So learning outcome is to solve the given problem. Now, this is the problem. A cantilever beam is loaded as shown in the figure, which is subjected to UDL of 10 kN per meter and a point force of 100 kN at the free end, and UDL is applied throughout the length of the beam. Now, for this problem, you need to solve the deflection and slope at the free end. At this end, we need to calculate what is the slope and deflection. Then, what is the moment and shear force at the salient points? That is what I need to calculate. Then, maximum deflection in the beam. Usually, in the cantilever beam, the maximum deflection will be there at the free end. That I need to calculate. Then, I need to calculate the reaction at the fixed support. So, these are the four quantities I need to find out. So before moving to the FM, let us try to solve this problem using mechanics of material. So when I go with the mechanics of material, first I need to calculate the reaction at the fixed end. So for that I need to use the static equilibrium condition to calculate the reaction. So for that, first I'll consider summation of Fy is equal to 0. So upward force, if it is any there, I'll consider as positive, downward I'll consider negative. Therefore reaction, let us assume it in the upward direction, so that I'll consider plus R, and this UDL is acting in a downward direction, so that UDL will be 10 into 4. So that is what I mentioned here, and this is vertical force acting downward 100 kilonewton, therefore it is minus 100. Therefore I have only one unknown, that is R, so that R can be calculated. R is equal to, it is 140 kilonewton acting in a upward direction because it is a positive value. Therefore whatever the reaction positive direction I have considered, it is correct. Similarly, I need to calculate the moment. For that, I'll consider another equilibrium, static equilibrium condition, that is summation of m at the fixed end is equal to 0. If it is making clockwise, I'll consider positive. If that moment is creating clockwise, I'll take it positive. So first is that UDL, it is 10 into 4, that is the force acting at a distance of 2 meter, because the entire length of the beam is 4 meter and it is spread over the all the 4 meter length. Therefore it is acting exactly at the center of the beam because it's a UDL force. Therefore the value is 10 into 4 into 2. It is causing a clockwise couple, therefore it is a positive value. Then 100 kilonewton is the force acting at the distance of 4 meters, so it is 100 into 4. That also creates the clockwise couple, therefore it is a positive value. Then once again, let us assume the reaction moment which is there at the fixed end causing a positive couple. So I don't know whether it is causing a positive or negative moments, so let us assume it as a positive, so it is plus m is equal to 0. Now when I solve this, I'll get m is equal to minus 480 kilonewton meter. So this negative indicates that it is not in the clockwise direction, it is in the anti-clockwise direction. Therefore it is 480 into 10 to the power of 3 Newton meter in the counterclockwise direction, that is anti-clockwise direction. So this is what the calculation of the reaction at the fixed end. So once the reaction is calculated, now I'll go with the first question, that is deflection and slope at the free end. That is what I need to calculate. For that, let us consider that equation of deflection, that is equilibrium equation of deflection. So that is ei d square y divided by dx square is equal to m. So let us calculate the moment at any section xx that is shown in the figure. Let us consider one section xx. At this section, let us calculate the moment. So that moment I have calculated here, it is r into x. So this vertical reaction which is acting at a distance of x from the section what I have considered, therefore it is positive value because it is acting in upward direction. Then this is the moment. Moment, it is not multiplied with the distance, but I need to put this moment in the form of x. Therefore it is m into x raised to 0. X raised to 0 is nothing but 1. Therefore it is only the moment, minus the applied UDL is throughout the span, therefore it is a negative value because it is acting downward direction. So it is 10 into x square divided by 2. This is what the moment which is acting about the section xx. So this force will not be included because I consider section up to this point. So whatever the force which are there on the section left hand side, only those forces I have considered. Then after simplification, by putting the value of r, by putting the value of m, so then after simplification I'll get the equation as this equation 1. By substituting whatever the value I calculated, this mxx, this value I am going to substitute in equation number 1. When I substitute that in equation number 1, I am going to get this equation. So this is ei d square by divided by dx square is equal to this equation. Now this I need to integrate. Now when I integrate, 1 dy by dx will be get cancelled, because this differentiation and integrations are uh, get cancelled. So I left out with ei into dy by dx. So this 140 into 10 to the power of 3 as it is, integration of x is x square by 2, minus 480 into 10 to the power of 3 as it is, x naught is, I mean x raised to 0 is x, then minus this 2, this 10 is 5, therefore I have simplified here, it is 5 into 10 to the power of minus 3, then x square is x cube by 3, plus integration constant c1. Now this is what dy by dx, this is what the equation of the slope, we call it as equation of slope because dy by dx is what my slope. Once again I need to integrate this equation number 3. So when I integrate, once again d by dx will be get cancelled, left out with y. So then this 2, this 140, it is 70 into 10 to the power of 3, x square is x cube by 3. Then this is 480, minus 480 into 10 to the power of 3 as it is, x is nothing but x square by 2. Then minus 5 into 10 to the power of 3 divided by 3 as it is, x cube is x raised to 4 divided by 4. Then constant as it is, integration of constant is x. Then for this entire integration constant is c2. Now in the next case I need to find out the value of c1 and c2. So for that I will consider the boundary condition at x is equal to 0, y is equal to 0. Therefore when I substitute x is equal to 0 in this y equation, I'll get c2. This value of c2 is 0. Similarly, to get the value of c1, I'll consider another boundary condition. When x is equal to 0, my slope is 0 because it's a fixed end. When x is equal to 0, I'll get a fixed end. Therefore at the fixed end there is no slope. Now when I substitute the value of x is 0 in this equation number 3, because this is what my slope equation, when I substitute the value of x 0, I'll get the value of c1, and that value of c1 is 0. Means my both the constants c1 and c2 are 0. So in the next case, now I need to calculate the deflection and slope. So that I need to calculate at the end of the beam. Therefore my total length of x will become 4 meter. So that x I need to substitute in equation 4 and 3. Equation number 4 I'll get deflection, equation number 3 I'll get the slope. Therefore from equation number 4, this is what my equation number 4, which is a deflection equation. So wherever x is there in that equation 4, I need to replace with 4 meter. So here this is 4 meter, this is 4 meter. After simplification I'll get that value is minus 2453.34. So therefore y is equal to, I know the value of ei, that is flexural rigidity, that is Young's modulus and moment of inertia. So that value I am going to substitute, so that I'll get the value of y is minus 0.0876 meters. So this is what my value of y, that is nothing but my deflection at the free end. Similarly I need to calculate the slope at the free end. Therefore for that I need to consider the slope equation. So in the slope equation, wherever x is there, that I'll replace with 4 meter. So these are the x value where I replaced with 4. Then after simplification I'll get minus 906.67 into 10 to the power of 3. Therefore my dy by dx is equal to that value divided by ei. So this is what ei I have taken here. This value of e and I, it is mentioned in the problem. Therefore after simplification, dy by dx is minus 0.03238 radians. So this is what my slope and this is what my deflection. That is what I have solved using mechanics of material. Next, second question is we ask you to calculate what is the moment and shear force in the salient points. So let us consider shear force at any section xx. Consider a section xx. Therefore it is now I'll consider the section from the right hand side. Therefore when I consider section, I'll get a force of 100 kilonewton and a small quantity of UDL. Therefore it is 100 plus 10 into x. Both are acting section right side downward. So section right side downward, both are positive. Therefore and now I need to put the value of x. When x is equal to 0, my shear force at point B is plus 100 kilonewton. Similarly when I put x is equal to 4 meter, entire length of the beam, I'll get a shear force at point A, which is plus 140 kilonewton. Similarly with the same section, let us calculate the bending moment. It is force into distance. Therefore it is creating sagging or hugging. Based on that I need to put the sign. So 100 kilonewton force, it sacks the beam. 100 kilonewton force, it hawks the beam. Therefore it's a negative value. It is multiplied with the distance. 100 kilonewton force is acting at a distance of x, that is from the section. Similarly 10 into x is the force. This is the force multiplied by distance. Now it is a UDL force. Therefore it is exactly acting at the center of whatever the section I have considered. Therefore it is x by 2. After simplification, it is minus 100x minus 5x square. It's a parabolic variation because I have an x square term here. Therefore, I need to know that parabolic variation by putting the value of x. Therefore, x is equal to 0, I'll get the value of moment at B, which is 0. Similarly, when x is equal to 4 meter, I'll get the moment value at A, which is minus 480 kilonewton meter. Now, coming to the third parameter, that is I need to calculate maximum deflection in the beam. So that maximum deflection we already calculated in the previous slide, that is y value, and that y value is minus 0.0876 meter. That is what the maximum deflection which is there at the free end, nothing but when x is equal to 4 meter. Similarly, this maximum deflection can also be calculated using the principle of superposition. That is, we know it is a problem where the cantilever beam is subjected to point force at the free end, and also it's a cantilever beam subjected to UDL throughout its span. It's a combination of two standard cases. Therefore, when I neglect the UDL force, now it is a cantilever beam with only point force at the free end. For that, the deflection at the free end is given by this equation, negative sign, because it is acting vertically downward. Similarly, when I neglect the point force and when I consider only the UDL, now in that case the deflection at the free end is given by this equation. So when I join these two equations by substituting all the values, I'll get the y, and that y is same as what we have calculated using the integration method. Now coming to the reaction, so this reaction, very first step, using the static equilibrium condition only we have calculated, that is R is 140 kilonewton and M is 480 kilonewton meter acting in a counterclockwise direction. Now this is what we have calculated using mechanics of material. Now basically we are dealing with FEM. This is I have done this mechanics of material I have done to compare whether FEM is giving the same value or not. For that reason, I have calculated the problem with the mechanics of material approach. Now we'll start with the solving the problem using FEM. First, I need to do the FEM model. So let us consider only one element of 4 meter length, and at node number 1 I have a vertical displacement v1 and applied force is f1, and similarly at node number 2 vertical displacement is v2 and applied force is f2. Similarly at node number 1 I have a what is that slope which is theta1 and applied moment is m1. Similarly at node number 2 I have a slope theta2 and applied moment is m2. So this is what FEM model. After creating FEM model, I need to calculate the element stiffness matrix. We know the element stiffness matrix for beam element is given by this. So this is already derived in the previous sessions. So consider that element stiffness matrix. Substitute Young's modulus and moment of inertia divided by length cube. When I substitute this, then here in the matrix I need to substitute the value of length of the element. Now I have considered only one element of 4 meter. Therefore, wherever LE I will substitute LE, and in some location I have LE square. So those LE square also I will substitute, and after simplification I will get it is 437.5 into 10 to the power of 3. That is the value of this what I have calculated. Then this 4 I will multiply wherever term it is associated with. So 6 4 are 24, like that I have multiplied and I obtained this matrix. Now this value is in terms of Newton meter, because all the values I have substituted in terms of meter, because this is in Pascal. Pascal is nothing but Newton per meter square, and this is in terms of meter raised to 4, that is moment of inertia, and length I have considered in terms of meter, that is 4 meter. Now after calculating this, now I need to calculate the global stiffness matrix. As I have only one element, therefore my element stiffness matrix itself becomes my global stiffness matrix. So this is what my global stiffness matrix. Now once I get the global stiffness matrix, now I need to calculate the equivalent nodal forces for the UDL force which is acting on the beam. For that we know it is a UDL force which is acting vertically downward. Therefore this is the equivalent nodal forces. We already done this in the third session. Therefore I have a one vertical force of Q0 into LE divided by 2 at node number 1 acting vertically downward. Similarly I have Q0 into LE divided by 2 vertically downward. Then I have a moment here which is Q0 into LE square divided by 12, negative value, and at node number 2 I have Q0 into LE square divided by 12, which is a positive value. Now I need to calculate those values. So let us calculate those values. Let us say this is the force which is there at node number 1 and this is the force, vertical force, which is there at node number 2. Both are negative. Therefore my F1 is equal to F2 minus Q0 into LE divided by 2. Let us substitute all the values of Q0 LE. Therefore I will get it is minus 20 into 10 to the power of 3 Newton. Now whatever the force I am doing here, that should be in terms of Newton or Newton meter. If it is a force, it should be in Newton. If it is a moment, that should be in Newton meter, because my left hand side I have a value in terms of Newton and meter. Therefore, when I calculate M1, it is Q0 minus Q0 into LE square divided by 12. When I substitute all the values, it is minus 13.33 into 10 to the power of 3 Newton meter. Similarly, when I calculate M2 at node number 2, the same value, but it is a positive value, therefore it is plus 13.33 into 10 to the power of 3 Newton meter. Now after doing this, I need to get the global force vector. Now to get the global force vector, I have F1 M1 F2 M2. So F1 M1 F2, along with F2 I have a point force, so let us add that point force at node number 2 and M2 as it is. So F1 is minus 20 into 10 to the power of 3, M1 is minus 13.33 into 10 to the power of 3, then F2 is once again minus 20 into 10 to the power of 3 plus P, the applied point force, is minus 100 into 10 to the power of 3 because it is acting vertically downward. Similarly, my M2 is a positive value, which is plus 13.33 into 10 to the power of 3. So after simplification, my F1 is minus 20 into 10 to the power of 3, M1 is minus 13.33 into 10 to the power of 3, then F2 is minus 120 into 10 to the power of 3, and finally my M2 is 13.33 into 10 to the power of 3. So after that, next step is to put it in equilibrium condition and applying the elimination method of boundary condition. So this is what my K and this is what my displacement matrix V1 theta 1 V2 theta 2, that will be equal to force matrix. F1 M1 F2 M2 is what my force matrix. Now I need to use the elimination method of boundary condition, where my node number 1 is completely constrained because it's a fixed end as a cantilever beam. Therefore at that location my displacements are 0, therefore v1 theta 1 is equal to 0. For that, what I need to do, I need to eliminate the first row first column. That is what elimination I have shown. I need to eliminate the first row first column, then I need to eliminate the second row second column. So after eliminating, I left out with 12 minus 24 minus 24 64. Outside I have 437.5 into 10 to the power of 3, left out with v2 theta 2, and that will be equal to minus 120 to 10 to the power of 3 and 13.33 into 10 to the power of 3. So that is what the left out matrix I have written here. Then I need to open this matrix to get the two equations, that is 437 1, I'll show it, 437.5 into 10 to the power of 3 into 12 into v2, then minus 437.5 into 10 to the power of 3 into 24 into theta 2 is equal to minus 120 into 10 to the power of 3. So this is what my first equation. Similarly, when I multiply this with second row, I'll get the second equation. I have two unknowns, that is v2 and theta 2, so that is what I need to calculate. So to calculate that, I need to solve these two equations using the calculator. Once when I solve these two equations, I am going to get the values of v2 and theta 2. So my value of v2 is minus 0.08762 and theta 2 is minus 0.03238 radians. So this is what my deflection and slope at the free end. Now I need to calculate the second parameter, that is moment and shear force. We know the moment matrix, so this is what moment matrix. Now I need to calculate the moment. To calculate the moment, let us first put x is equal to 0. It means I need to calculate the moment where x is equal to 0, that is the value of zeta at x is equal to 0 is plus 1, nothing but it is at the free end. I am calculating the moment at the free end. Therefore I need to substitute the values of ei divided by le square. That is what I have done. Wherever zeta in this matrix, I need to substitute plus 1. When I substitute plus 1, I'll get these values. Then displacement, I already know the displacement, v1 theta 1 both are 0 because it's a fixed end. v2 theta 2 just now we have calculated in the previous slide, so that I am going to substitute here. So after simplification, I am going to get the moment, which is 13.37 kilonewton meter. So this is the moment which is there at the free end. Now when I come to the moment at x is equal to LE, nothing but at x is equal to 4 meter, nothing but it is at the fixed end. So at the fixed end, I have the value of zeta is minus 1. So similarly, when I substitute all the values here, I am going to get the value of moment. That value of moment is minus 466.69 kilonewton meter. Then next is I need to calculate the shear force. So this is what my shear force matrix. So here I need to substitute once again the displacement values. Then I need to substitute the length of the element. So then ei divided by le cube, these are the values I need to substitute. then I'll get the shear force, and that shear force is 120 kilonewton. So this is what the value of shear force. So I have calculated the second parameter, that is moment and the shear force. Now I'll come to the third one, that is my maximum deflection in the beam I need to calculate. For that I'll consider the deflection equation using the shape function. So this is V is equal to N1 V1 LE by 2 N2 theta 1 plus N3 V2 plus LE by 2 N4 theta 2. So this is my deflection equation with the help of shape function. So let us substitute the values of N1, N2, N3, N4 in the above equation in the form of zeta. Then we know that the maximum deflection in the beam will be there at the free end. There at the free end, my value of zeta is plus 1. Therefore, in the above equation, wherever zeta, there I need to substitute plus 1 along with whatever the displacement value we have calculated. V1, theta 1 both are 0 because it's a fixed end. V2, theta 2, these are the two values we have obtained. So that I need to substitute. So first V1 is 0, therefore multiply with this term, it will become 0. Then theta 1 is also 0, therefore my second term is also 0. Here I have a value for V2 which is minus 0.08762. Wherever zeta I substitute plus 1, I obtained this. Similarly, wherever zeta I substituted plus 1, and my value of theta 2 is minus 0.03238. So that is what I have substituted. After simplification, I'll get the maximum deflection in the beam which is minus 0.08762. That is what the value. Now once that is done, I need to calculate the reaction. We know to do the calculation of reaction, we need to consider the eliminated rows. So if I consider the first eliminated row, I'll get the vertical reaction R, and if I consider the second eliminated row, I'll consider the moment reaction M. So this is my first eliminated row. So that is what I have considered along with whatever there on the right hand side. If I take it to the left hand side, it will become minus. So I have a value for that. So when I substitute all those values and do the simplification, I'll get the reaction at the uh, fixed end which is 140 kilonewton meter. Similarly, consider the second eliminated row and consider my right hand side to the left hand side, it will become minus M1. Therefore, after substituting all the values, simplification, I'll get the moment reaction which is there at the fixed end. It is the value of 480.02 kilonewton meter. So these are the reactions we have calculated. Then now we can do the comparison what we have done with mechanics of material and FEM. So these are the four parameters we have calculated. So when I come to the MOM, the deflection and slope is 0.0876 meter and meter, and my slope is 0.03238 radians. So if you see the values in FEM, I obtained the same thing. When I calculate the shear force and bending moment values at the salient points, I am going to get the values of shear force at A and B and bending moment at A and B. These are the values. But when I come for the FEM, I have converted applied UDL into equivalent nodal forces. Therefore, there will be a slight variation in the values. But when you consider the addition or deletion of those according to the sign, I'll get the same value because I have a shear force of 120 kilonewton, and these are the two moments which are acting at free end as well as at the fixed end. I have only one shear force, that is average shear force, which is there in the beam. That value is 120 kilonewton. Then coming back to the maximum deflection in the beam, that is third parameter, that is minus 0.0876. Here also FEM I obtained the same value. Then last one is reaction. So these are the two reactions I have calculated in mechanics of material, and I am getting the same two reactions in FEM. So this is how we can solve the problem in case of beams. Thank you.